Welcome to Lecture 6.1, the heat and wave equations on the real line. The broad goal of this lecture is to solve an initial value problem for the heat equation on the real line. So here's the same old heat equation that we know and love. We have an initial condition, except now x can be any real number. So I say initial value problem because there are no boundary conditions here. That said, sometimes we can prescribe a boundary condition, like or a sort of a pseudo-boundary condition. We might say that the limit as x goes to plus or minus infinity is 0. Realistically, there can't be an infinite amount of heat, so something like this. However, often we don't need to do that because if h of x is such a function anyways, and we know what's going to happen to something like this. We don't know exactly what it's going to happen, but somehow the heat is, well, that's supposed to go underneath. Somehow the heat's going to dissipate like this. So often these things are built in or implied. We don't necessarily have to specify them. So problems like this are called Cauchy problems. After that, we will do the same thing for the wave equation. Though you may remember, when we first introduced the wave equation, we actually did it with an unbounded domain. So this is something that we've seen before. The process for solving this initial value problem consists of two steps. First of all, we will solve an easier initial value problem. So instead of a general function here, we will solve the same problem except where that function is the Heaviside function, or just a unit step function. That's another name for it. And then next, we will construct a solution to the original initial value problem using our solution to the previous part. Let's start right away with the initial value problem above. The first step is to solve a similar IVP for the heat equation on the real line, except the initial condition, instead of being a general function, lowercase h, is the Heaviside function, or a unit step function, capital H. So I'm going to use v for this function because it technically is a different function than the u that satisfies this initial value problem. Okay, so let's get started. Here is that same initial value problem. You may notice that I stuck in a constant v naught here. And I'm going to set this equal to 1 pretty soon. So you may wonder, why did I do this? Well, I actually do want to use this symbolically pretty soon. You'll see why. It'll make sense. Okay, so to start, it's not clear at all how are you even going to approach this. So to motivate that, I want you to take a look at the units of all these quantities, Vt, c squared, Vxx, V, this thing, and so forth. And then we're going to make an argument about dimension analysis. Let's say that distance is measured in meters, and time is in seconds, and temperature, of course, is degrees. Then the units of Vt, the time derivative, is degrees per second. The units of Vxx are degrees per meter squared. So since the product of Vxx and c squared is Vt, that forces c squared to have units m squared over, or meter squared over seconds. And of course, V has units degrees, and so V naught, which is this constant, has unit degrees as well. And what I didn't write down that you know are x has units meters and t has units seconds. Here's why we care. If we take v of xt, this function, and divide it by the constant v naught, then that is dimensionless. And the other dimensionless quantity in here is x divided by the square root of 4c squared t. So let's just check that. So x is in meters, and square root of 4, well, c squared is meters squared divided by seconds, and then t is in seconds. So these things cancel. The meters cancel. We really shouldn't have put the 4 in here. So why is the 4 here in the first place? Well, that's purely for a notational convenience. is going to make things cancel out nicely down the road. You don't need to worry about it now. It's not necessary. It's just easier this way. The other question you may be wondering is, why did I put a root 4c squared here? That's just 2c, right? Well, first of all, most books probably write the heat equation as k vxx, where k is positive. I've been sticking with c squared to match what we see in the wave equation, just for consistency. So because of that, most books have this quantity root 4 kt, and so I just want to keep this for consistency. I mean, you are certainly welcome to make this a 2c if you want. Okay, so we have these two dimensionless quantities, v over v naught, and so we can express one of them as some unknown function of the other. And so that's what we have done here. So v over v naught is some unknown function f of x over root 4c squared t. For simplicity, I'm going to set v naught to be equal to 1. Again, I didn't really have to do this in the first place, but I wanted to simply because I felt more comfortable saying that v naught is in degrees than to say that 1 is in degrees. That would be kind of weird. I guess I could have said h of x is in degrees, but then dividing by h of x, that feels weird as well, because sometimes that's 0. So really, I just felt more comfortable writing v naught so I could say that that is in degrees. So if we set this equal to 1, then what we get is this is v, which is some function f of, I'm going to call this z. So we're going to change variables, call this quantity z. So v, which is remember v is what we're trying to solve in the first place. That is some unknown function of z, where z is x over root 4c squared t. Now we can use the chain rule to compute the partial derivatives of v that we need to plug back into this PDE. So let's start with Vt. So Vt, the time derivative of v, is just the derivative of f times the time derivative of the inside, z. So let's compute that. So z is x over root 4c squared times t to the minus 1/2. I still need to do this anytime there's a function like this. I need to write it out basically. So now the time derivative, z t, is negative 1/2. Maybe some of you are better at doing this in your head than me. Negative 1/2 x over 4c squared t to the minus 3/2. Okay, so this simplified is f prime of z. Actually, let me do this. Let me put the negative 1/2 first, just because it's more natural. So I'm going to say negative 1/2 x over root 4c squared t cubed, because that's a t to the negative 3/2, times f prime of z. Okay, next, let's do one at a time. So vx is f prime of z times the x derivative of z. So let's see what that is. Well, so that's a little bit easier to compute because x is right here. Yeah, x is right there. So the derivative of that is just going to be a constant. So zx is 1 over root 4c squared t. Okay, so this is just going to be 1 over 4c squared t. Okay, so, I forgot, times f prime of z. And now the second derivative of this, we just do the same thing. We take the derivative of this thing. Thank goodness that there's no x in here. That's just a constant. So otherwise we'd have to do the chain rule again, or not the chain rule, sorry, the product rule. But so let's So this is 1 over 4c squared t times f double prime of z times zx, which of course is just this thing here, so this simplifies as 1 over 4c squared t, because we have 1 over root of that times 1 over root of that again, times v double prime of z. Okay, so the derivatives that we need, the partials to plug in, are this one and that one. Okay, we are now ready to plug this in to our PDE. Recall, we're trying to find v, which is a function of x and t, but by changing variables, we're writing it as a single variable function f of z, where z is in terms of x and t, namely x over root 4c squared t. And we just found vt and vxx moments ago. So let's get started. The left-hand side of the PDE is vt, which is negative 1/2 x over root 4c squared t cubed f prime, and set that equal to c squared vxx, which is 1 over 4c squared t times f double prime. So right away the c squareds cancel. This t I'm going to write as root t squared, and that's going to reduce this exponent t cubed down to a t to the first. And if we do that, this should look familiar. That is just equal to z right there. So now we can multiply this 4 on the left hand side to get a negative 2, and we get negative 2z f prime equals f double prime. And this is something we can solve. Remember how to do that? Well, it's a second order ODE. Unfortunately, it's not constant coefficients, so you might think power series method. However, it's not that hard. This is really in spirit just a first order ODE because there's no f. In other words, what we can do is we can let g of z be f prime of z, and then g prime is just going to be f double prime. So if we do this, this becomes negative 2z g equals g prime, and this is something we can solve using separation of variables, among other methods. So dg dz is negative 2zg. We move all the g's to the left side, we get dg over g is negative 2z dz. We integrate both sides. And then the left-hand side is the natural log of g, and the right-hand side is negative z squared plus c. Now if we exponentiate both sides, we get g of t is c1 e to the negative z squared. Of course, I'm skipping a step here, but this is child's play by now. So if g is this function, oh, I said g of t, that's just a habit. Let me fix that. G of z. So f is the antiderivative of g. So f of z is, let's integrate this by the fundamental theorem of calculus. So we're going to integrate out, we don't want to integrate out the z, so let's go from 0 to z of g of r dr. So this is the integral from 0 to z, well, let's put a c1 there, of e to the negative r squared dr. And remember, this is one of those irritating functions that doesn't have a nice antiderivative form. So let's just leave it like that. Now we need a second constant of integration. So let's put that there, C2. And so we're almost done. Let's just remember what z is, and let's plug z back into here. So v of x and t is just the same function. And it's the same thing here, but z we're going to put in this. So it's the integral from 0 to x over root 4c squared t e to the negative r squared dr. I forgot my constant again, c1, and then plus c2. Okay, so that is the general solution. And I guess there's not much left here. I want to actually figure out what C1 and C2 are, because we can use this initial condition. And I probably could have fit it in here, but I think I did make another slide for this, thinking it would take up more room. And it's probably good to pause and summarize and utilize that slide. Okay, so here we are. We want to solve this initial value problem for the heat equation, and we already have the general solution. So all that's left to do is plug in t equals 0 and use this initial condition. So first of all, let's recall what this function is, the Heaviside function. It's 1 when x is positive, and it's 0 when x is negative. And it doesn't really matter how we define it when x is 0, but let's be consistent and say that it's equal to 1, because I think that's what we did earlier in this lecture. Now, there are settings where it does matter, but nothing in this class. Okay, so there's two cases. We're going to plug in t equals 0 and either set this equal to 1 or to 0. So we have to do those separately. So start when x is negative. In this case, v of x0 is c1. Now the integral, well, technically this is undefined because we're plugging in 0 to the bottom of the fraction. We're dividing by 0. But we're adults. We know how to handle this. It's an improper integral. You got to use a limit. And we all know what we're going to get is that this limit up here is a fixed negative number divided by 0 is going to be negative infinity. So we're integrating from 0 to negative infinity of e to the negative r squared dr plus c squared. We have to set that equal to 0. Now this thing here, remember that there is no closed form for the indefinite integral of this e to the negative x squared, but you might remember from either your Calc 2 class at the very end, when you learned about polar coordinates, or vector calculus, that surprisingly, the definite integral of this function over the whole real line, let's call it e to the negative x squared, surprisingly equals root pi. I was going to write root pi over 2, but I think it's just root pi. So remember, this thing looks like a bell curve, and the trick was if you switched into polar coordinates and you get a double integral, that this thing falls right out. Okay, so this is going to be root pi over 2, well, almost, or actually, so this is half of the bell curve, but we had to be careful because we're integrating from 0 to negative infinity, so we're integrating backwards. So, in other words, this is negative c1 integral from negative infinity to 0, e to the negative r squared dr plus c2 equals 0. So this is negative c1 root pi over 2 plus c2 equals 0. So that is our first equation. And then our next equation is coming from when x is positive. So in this case, if we plug in t equals 0. Once again, it's technically not defined, but we know what we can do is x is positive and we're dividing by 0. So we get integral from 0 to positive infinity of e to the negative x squared dx. And this, again, this is just, oh, I said dx, I should say dr. That's another one of those just habits. Plus c2 equals 1. Okay, so this first equation tells us that c2 equals c1 root pi over 2. And the second equation says that c1 root pi over 2 plus c2. So plus c2, I'm going to write that as c1 root pi over 2 equals 1. Okay, so that means that c1 root pi equals 1. So c1 equals 1 over root pi. You know, I'm glad I didn't try to squeeze this into the last slide. This is much better. So c1 is 1 over root pi, and then c2 is c1, so this thing times root pi over 2. So c2 is, that's just going to give us 1/2. Okay, so now we have our final solution. So V, our particular solution that satisfies the initial condition, is, I'm going to write it as, let's see, yeah, I'm going to write it as 1/2 plus 1 over root pi times the integral from 0 to x over root 4 c squared t e to the negative r squared dr. And that's one way to write this. Now, as often the case in mathematics, when there's a function that arises in many settings that doesn't have a particularly nice closed form, something like this, you often give it a special name, something like sine or cosine or logarithm. We've seen some new ones in this class, like we've seen Bessel functions. We've seen the sampling function when we looked at Fourier transforms. I think we've seen Chebyshev polynomials, Legendre polynomials, and a few others. So in statistics, there's a, let me use this little space. So in statistics, there's a function called the error function, or ERF for short, which is 1 over root pi times the integral from negative x to positive x, e to the negative t squared dt. Now, here's the bell curve with the Gaussian distribution. What this actually represents is the area under the curve from here. So it's the probability that a random variable is going to fall between negative x and positive x. And so the name error function corresponds to we're disregarding the everything outside of there, which is the tail. So of course, by symmetry, we can write this as 2 over root pi times integral from 0 to x of e to the negative t squared dt. So that should remind you a lot of this thing here. So if we factor out a 1/2, and we write this as 1/2, 1 plus, now we have a 2 over root pi here, and this is that error function at where this variable, instead of being x, it's this thing which is z. So I'm going to write this as the error function of x over root 4 k t. Now before we move on, I want to explain why this solution makes sense. Before we do that, let's look at this Heaviside function. Maybe I should have drawn it a little bit bigger, and think about what does happen physically if the heat is distributed like this initially. Well, it makes sense that when T is small, the heat will probably look something like that. When T is a little bit bigger, it'll spread out more and it'll get something like that. And again, in the long run, it will approach the steady state solution of a constant 1/2. So the ERF function, remember, as a function of x, it is just the area of this under this curve, so the normalized area. So as x goes to infinity, it approaches 1, and then as x approaches negative infinity, it goes to -1 because you're integrating backwards. So the sign flips. So the ERF function looks like this, and these asymptotes are 1 and -1. So if we add 1 to it, we're going from 0 to 2 instead of -1 to 1. Then we divide by 2, we're going from 1 to 0. So what this looks like is, this function should look like this, 0 to 1. So for a small t, this ERF of this is very, so this argument is very small. Sorry, the denominator is very small, so this whole thing is very large. It's close to infinity. So for small t, this is going to go to 1 pretty quickly. In other words, let's just fix a point x naught here. Again, when t is really, really small, then this is going to be large, and this value is going to be very close to 1. Then as t gets larger and larger, this thing gets smaller and smaller, so this area here is shrinking. And so it's going to go downwards as t gets larger. So maybe that's one value of t, then it's for a little larger value of t, it looks like this, then it looks like that, and so forth, and eventually it approaches a flat line. Now that we have solved the heat equation on the real line where the initial condition is the Heaviside function, it is relatively straightforward to adapt that to solve the heat equation with an arbitrary initial condition. Let's call it lowercase h of x. To see why, we'll start with some simple observations. First, let's take the function that we just found in the previous slide. This v of xt is a solution to the heat equation. And I'm not looking at initial conditions, just the plain old PDE. Next, if I have any function v that solves the heat equation, then so does the derivative vx. And it's relatively easy to see why. Well, let's see why that works. So let's take vx, and so what does it mean to solve the heat equation? It means that the time derivative of this minus c squared times the second spatial derivative of this equals 0. That's what we're trying to show. Again, I just moved this right-hand side to the left-hand side. And, well, how can we write this? Well, the order of derivatives doesn't matter. So vxt is the same as vtx. So I can write this as vt minus c squared vx x, in parentheses, x. Can't stop me from doing that. And of course, this is 0 because v solves the heat equation. So this is 0, showing that vx solves the heat equation as well. So putting this together, we get that the derivative, the x derivative of this thing that we just got, is a solution to the heat equation. Now, do you remember how to do that? It's the fundamental theorem of calculus. So of course the derivative vx of xt, this first term, that's a constant, that's just going to go to 0. And then the next term, well, we have an integral here, So the derivative cancels the integral, but we have to, by the chain rule, we have to take the derivative of this top part with respect to x, right? So that's just, well, there's just a single term x here, so we just take this constant. So let me write that down. So 1 over root pi times 1 over root 4 c squared t, and then we're going to integrate. Oh, I'm sorry, we don't integrate because the derivative cancels the integral, but what we have to do is we have to put this top thing in the exponent r right there. So it's e to the negative x squared divided by the square of root 4c squared t, so 4c squared t. So this solves the heat equation. Let's write this function that we just got as capital G of xt. This is sometimes called the fundamental solution to the heat equation, which I'll explain momentarily, and it's also called the heat kernel. And the word kernel comes from kernel of the linear operator, because you can think of it as it is a function in the kernel of d dt minus c squared d squared dx squared. So the heat equation is, if this, let's call this linear operator L, is the equation LU equals 0. So solutions to the heat equation are precisely functions that are in the kernel of L. Okay, so before we move on, let me explain what this looks like and what this represents. So of course this is a bell curve centered at 0. So the area under the curve is going to be 1. So at some point in time, let me sketch this. It might look like this. It's hard to draw this accurately. So this might be g of x. Let me call this t2. I'm going to go back a few steps. So if we go later in time, another snapshot, it's going to be more spread out like this. So this might be g of x t3. So t is increasing this way. If we go back in time for a smaller value of t, it might look something like this. So this is g of x t1. If we go further back in time, it's going to be really steep. So maybe this is g of x t0. And so think about what happens at t equals 0. So at t equals 0, well, the area under each of these curves is 1. So at t equals 0, of course this isn't defined, but in the limit, and I'm hand waving a little bit, but if you've taken your ODE's course, and remember Laplace transforms, this should ring a bell. This corresponds to the delta function centered at 0. That's the function that is 0 everywhere and infinity at a single point and somehow has an area of 1 under the curve. If you haven't seen this before, then you haven't taken the full prereqs, and so go look at my lecture on the delta function in my differential equations class. It's in the section of Laplace transforms. Okay, so this is called the fundamental solution to the heat equation because it represents the solution where the initial condition is this thing, where you literally put 1 unit of heat at the origin and then let time proceed and see what happens. Now, the antiderivative of this function, which is this thing up here, which is what we got in the previous lecture, recall that represented the solution where the initial condition was the Heaviside function. So in the previous slide, we solved the heat equation where the solution is the Heaviside function. And in this side, we said, well, let's make our lives easier. Let's take the derivative of that solution. And that's also a solution, and it represents this thing here. And you may recall from differential equations, you study Laplace transforms, that the delta function can be thought of, loosely speaking, as the derivative of the Heaviside function. Again, it's 0 everywhere and infinity at this point of discontinuity. And so similarly, this function this fundamental solution is the derivative of the function that we derived in the previous slide, which is right here. So hopefully you should be seeing some of these connections, and it should make sense as to what this thing represents physically. So the big idea is that without initial or boundary conditions, the solution to the heat equation is just a bell curve. Finally, I want you to consider the function g, but shifted by y. So g of x minus y and t. This solves the heat equation. That makes sense intuitively because it's just a shifted version of the bell curve, and on an infinite line, any two shifts of the bell curve look exactly the same. Analytically, well, these things have the same x derivatives and t derivatives, so if one solves, the other one will solve. Okay, so we've established that any shift of this solves the heat equation, and this represents an initial unit heat source at y, which is not necessarily 0. So let me draw this here. So this is x, and y might be something here, and this is going to represent, and this delta, so think of it like a delta function here. Okay, so now when we had a bounded domain, and we got a solution of the form u of n of xt, what did we do? Well, we took some linear combination of these solutions, and we said, well, as long as this integral exists, this is going to be a solution as well. So in this case, we have g of x minus y t. So y is now the variable that's changing, although it's going to change continuously instead of n, which changes discretely. So we can multiply this by some scalar. Let's call it h of y. We normally represent functions of a discrete variable with subscripts and a continuous variable like this. And of course, the continuous version of a sum is an integral. So as long as this integral over potentially the whole real line exists, then this is a solution as well. Okay, so what happens at time equals 0? Well, I claim if you plug in time equals 0, you're going to get this function h back. So I'm not going to verify that all the technical details for the same reason that I skipped them when we did Laplace transforms, and there's some technical details about the delta function and continuity, but if you're interested, I encourage you to look them up yourself. So if you take the limit of this as t goes to 0 from the right-hand side, what you get is the integral from negative infinity to infinity of h of y, and now this g, well, if t is very, very small, then this is going to look like a, no, I'm not drawing this well at all, sorry about that, it's going to look like a very skinny bell curve. So in the limit, this approaches the delta function. So this is the delta function shifted by y. And if you remember your Laplace transform days, then this, if you multiply the delta function, now here y is the variable that we're integrating out, by a function, that just picks off the value of h. So this is equal to h of x. And this holds for all x. So this function, this function here is the particular solution that satisfies, to the heat equation, that satisfies this initial condition. So we've done it. We've solved the heat equation, an initial value for the heat equation on the real line. In summary, the solution to the initial value problem for the heat equation on the real line, where the initial temperature is a function h of x, is the integral from negative infinity to infinity of that function h of y, which we will integrate out, times 1 over root 4 pi c squared t times e to the negative x minus y squared divided by 4 c squared t dy. An alternative form of this solution is called the Poisson integral representation, which is seen here. Let me show you how to derive that. So if you look at the original solution, the exponent is pretty nasty. So let's call this thing r squared. If you remember when we were deriving this a few slides ago, at one point this was negative r squared. So we can do that by saying r is equal to x minus y divided by root 4c squared t. And if we do that, then the derivative dr dy equals negative 1 over 4c squared t. X is just a constant. And so we get that dy equals negative root 4c squared t dr. So we're going to plug that in for dy. And finally, we have to plug something in for y as well. So from this thing right here, we get that y equals, let's say we can multiply this by r, and we get r times root 4c squared t. Well, we got to actually make this negative because there's a negative y right there, and then plus x. So notice that this term, this is y, that goes right in here. This exponent becomes negative r squared. And finally, when we substitute in for dy, this negative root 4c squared t cancels with this thing here, so the coefficient now is just 1 over root pi. So this is just another way to write the same thing. We'll conclude this lecture with the wave equation on the real line, which is something that we've actually seen before. This is how I introduced the wave equation, how I motivated it in the previous section. So recall from that the solution to the wave equation, the general solution to the wave equation, that's before we put any boundary or initial conditions, is of the following form. It's big F of x minus ct plus big G of x plus ct, where f and g are arbitrary functions. I don't mean to tie these to these functions little f and g that I have for initial conditions. These are different. So let me sketch what that looks like. So if big F is a function like this, think of it like a signal. Oops, let me not do that. Let me do it like this. Then f of x minus ct represents that signal at moving at speed c to the right and a distance ct away. Now if big G of, let me draw this a little differently, if g of x is some other signal, then g of x minus, I don't know if I drew that well, so this is g of x plus ct, not minus, that is traveling at speed c to the left, and at time t is a distance ct away. So this is just saying that you take any function traveling to the right and superimpose it with the one traveling to the left, that solves the wave equation. And we also finished that lecture by doing a specific initial value problem. I said, suppose the initial position is lowercase f of x, and the initial velocity, in that case, if you remember, I said, let's suppose it's 0. So this, let me draw a picture of this. So here we have a function, let's just say f of x, and then at time t bigger than 0, the solution was, so intuitively it's going to split half left and half right. So this is 1/2 f of x minus ct, and this is 1/2 of x plus ct. That should make sense physically. And indeed, the general solution is u of x t, 1/2 f of x minus ct plus f of x plus ct. And it's easy to check that. Again, if you plug in 0, you get f of x. And if you take the derivative of this, you do get 0. So now I'm going to modify this, and add an arbitrary initial velocity, let's say function g of x, and I'll just tell you what the solution is. It's going to be plus 1 over 2c times x minus ct, or times the integral from x minus ct to x plus ct of g of s ds. So again, it's easy to check that if you plug in 0, this term is also 0. That doesn't affect this initial position because you're integrating something from x to x. Of course, that's going to be 0. And it's easy to check that if you take the t derivative, let's see what happens. So these first two terms, this is 1/2. If you take the t derivative of this, you get f prime of we're going to plug in t equals 0, so f prime of x times the derivative with respect to t, so that's negative c. And then the time derivative of this term is going to be f prime of, and it's going to be f prime of x plus ct, plug in 0, f prime of x, times, by the chain rule, the t derivative of the inside, so that's going to be times c. These, of course, cancel. And now the derivative of this term is by the fundamental theorem of calculus. So it's 1 over 2c. And so now we have g of x plus ct times the t derivative up here. So that's going to be times c minus g of x minus ct times the t derivative down here. That's going to be a minus c. And of course we're doing this at t equals 0. I should say that over here too, at t equals 0. So let's see, these c's are going to cancel. I think everything should cancel. We got a plus plus, the c here cancels the c here, and so yes, we have 1/2 of, well, this becomes at t equals 0 g of x, so that's 2g of x divided by 2, and this indeed equals 0 plus 0 plus g of x. So this indeed is, so let me box this. So this indeed is the solution to the most general initial value problem for the wave equation. It's often called D'Alembert's formula. And finally, let me conclude by comparing what happens with the heat equation and the wave equation. Of course, you know, with the wave equation, signals propagate. An initial signal like this just moves, well, I guess it moves left and right. I didn't put arrows here, maybe I should. Whereas if this were the heat equation, the signal would, let me just draw it over this. If there were the heat equation, the signal would dissipate and get spread out and get lost and eventually go to 0. Okay, that's a great place to stop. What we will do next time is we will look at the heat and the wave equation on half-infinite domains. So where x goes from, say, 0 to infinity instead of the entire real line. Stay with us.